This lesson introduces control signals, another important feature in AudioWeaver. First of all, they're defined as having a block size of 1. So instead of having an entire block of data, it's only operating on one sample. They're drawn as dashed lines in designers, and there's really two ways of getting control signals. One, using source modules, very often a DC source or a sine wave generator. You can specify the output block size as 1. Or they're generated as intermediate results from the block statistics module or the RMS modules. Once you have a control signals, pretty much all the modules in AudioWeaver can operate on control signals. You can scale them, you can add them, you can filter them, and so forth, whatever you want to do. There's a few special controllable modules. These are used very often. There's a second order filter control, so that allows you to vary frequency, gain, or Q with a control pin. And there's also a scalar control, where it's adjustable control scalar, and the scaling is based on the value in the control pin. It also turns out you can use the paramset module, and you can turn any module into a controllable module. Let's now go look at two different examples of control signals. First example we're going to look at is part of the auto amp example. So this is an automotive system, and you'll notice here that there's a volume knob. So this is a slider that lets me set the volume setting. It goes from 0 to -60. And if you look at the arguments, we specify number of channels 1, block size 1, sample rate of 750 Hertz. 750 Hertz is based on the input pin, where we have 48 kilohertz divided by 64 is 750 Hertz. So this dashed line holds a single sample of data. We're going to take a look inside the DSPC volume subsystem. This subsystem implements a Fletcher-Munson volume control. You'll see the volume input here is the dashed line. It goes through two table interp modules. So these modules will convert from the volume setting to the amount of bass boost, and the other one does similarly volume setting to the amount of treble boost. So the output here is the number of dB that we want to boost the low frequencies. And over here we're using the second order filter control high precision. It's configured to be a peaking EQ, and we want to take the gain from the input pin. So these values get updated every block, but there's only a single sample. And then here the wired data is an entire block of data. Similarly on the output, we also apply the final gain using a scalar control module. So this is the first example that we're going to show. Let's look at a second example of how control pins are used. This is an SPL meter, and control pins are used in two places. One, we have a DC source that's setting the sensitivity of the microphone. This is a control signal that's input to the subsystem. And if we navigate in the subsystem, you'll see that the RMS module also generates a control signal. So let's look at the wire data. So the input to the RMS module is 96 samples at 48 kilohertz. That's a 2 millisecond block. And so the RMS module computes the RMS value and does filtering, and it outputs a single sample. Since it's a 2 millisecond input block, the output sample rate is 500 Hertz. So this is one sample, one channel, and you can see that it's drawn as dashed lines here. So control signals are good for controlling other modules. They're also good for doing decimated processing, and control signals are more efficient because we're only operating on a single sample. You'll also see that once we're in the control end, we can use all the typical audio modules as before for manipulating control signals.